The very next topic is indicator diagram, which is to be discussed in detail. This is quite an important section to understand thermodynamic processes. For indicator diagram, we can state that this is a graphical representation of a thermodynamic process. A thermodynamic process can be graphically plotted as indicator diagram. We know that thermodynamic processes are basically used in changing the state of a gas. For the state of a gas, we define thermodynamic coordinates which are written as pressure, volume and temperature, and combining the three coordinates we get the state of a gas. Either of these coordinate changes, the state of gas will also change. So now as we are studying indicator diagram, let's analyze what exactly is indicator diagram and how it is drawn and what are the properties of an indicator diagram. So we can simply write properties of an indicator diagram curve. There are a lot many things we are going to study about indicator diagram. The very first thing about ID we can state that ID is generally plotted between pressure and volume of a gas, and each point on ID represents a unique state of gas. Like if we draw a simple indicator diagram, always remember in general indicator diagram we take pressure on y-axis and volume on x-axis. So we just plot a point. This point gives us a value of volume and a specific value of pressure. Say these are P1 and V1. So using gas law we can find out the temperature, which can be given as PV over NR. If we know the pressure and volume of a gas, we can easily find the temperature T1 corresponding to P1 and V1. So this is the point where temperature is T1. So we can say this point on this indicator diagram, which is plotted between P and V, this point is giving us the idea about the state of a gas. That's why we have written each point on indicator diagram represent the unique state of a gas. Another characteristic about an indicator diagram is we can write a thermodynamic process of a gas is represented by a curve on ID between two states of the gas. Like for an example, there is an ID curve plotted between pressure and volume, and so we are having a state 1 where the gas pressure and volume are P1 and V1. And temperature is T1. This is the state 1 of the gas. And see, the state of a gas is changed from S1 to S2, where volume becomes V2 and pressure becomes P2. So to change the state of gas from S1 to S2, we need to execute a thermodynamic process by which gas will be going from state 1 to state 2. Now in this situation, there are infinite ways to execute this process. Like initially we'll keep the pressure constant and we change the volume of gas from V1 to V2. In that case, the gaseous state will change from S1 to some intermediate Si dash, where this straight line will be showing us the locus of all the points which are representing the state of gas when isobarically the gas is taken from a state S1 to Si dash. Now, keeping its volume constant, we increase the pressure. So you can say this will be the curve which will plot. So this is a path along which the gas is taken from initial to final state, which is composed of one isobaric and one isochoric processes. This is path 1. Similarly, we can initially keep the volume constant and increase the pressure, and the gaseous state is changed from S1 to Si. And now its pressure is kept constant and its volume is increased. Then also you can see there is another path. This we can call path 2, along which also we are changing the gaseous state from S1 to S2, but the path is altogether different. It is also possible that from S1 to S2 the gas is taken directly and both pressure and volume simultaneously varies, and say the path would be like this. Say this is path 3. So we can say a path gives us the locus of all the intermediate states of the gas in a thermodynamic process when gaseous state changes from S1 to S2. So we can simply call ID curve is the locus of all intermediate gas states from one state to another in thermodynamic process or processes. Either we can say like in path 1 and 2 we can see this path is composed of two processes. One is isobaric, other is isochoric. It may have another kind of paths like S1 to some Si1 where the volume is excessively increased and pressure is decreased, and then the gas is taken to S2. This is say the path 4, which is also composed of two separate curves, or you can say this path 4 is including two different thermodynamic processes according to which we are changing the gaseous state from S1 to S2. So always remember in a thermodynamic process, or we can state in case of plotting an ID curve for a gas from S1 to S2, always we use the locus of all intermediate state, and this curve also gives in between S1 to S2 at any point. If we use the volume, this curve will give us the pressure correspondingly. The next characteristic about an indicator diagram is we can say for changing the gas state from one to another, the curve plotted between two states, which we already discussed the locus of all intermediate states, is having an equation called process equation of the thermodynamic process being executed. More precisely, we can say if a gaseous state is changed from initial to final. So this was the initial state where pressure, volume were P1 and V1, and the gaseous state is changed to S2, where corresponding pressure and volumes are P2 and V2. And say a gas is taken from a state S1 to S2 corresponding to a thermodynamic process which is shown by this curve. then obviously this curve as it is plotted according to a process between pressure and volume, it must have an equation which is P equals to f of V like y equals to f of x. Now in this situation, this equation P equals to f of V is the relation between pressure and volume. It is actually the instantaneous relation between pressure and volume corresponding to which the gaseous state is changed according to a specific thermodynamic process. So this P equal to f of V, this is termed as process equation for the thermodynamic process. The process according to which the state is being changed, it is relating the pressure and volume at any instant of the gas. Here be careful, we assume that at every instant the gas is in equilibrium. That means at a particular volume we can define a particular pressure. This phenomena we ideally define as quasi-static processes. We already discussed as well as we'll discuss it specifically in detail. Another important characteristic of indicator diagram is for a thermodynamic process, work done by the gas can be calculated as we already discussed, the work done is written as integration of P dV from V1 to V2 if the gas volume changes from V1 to V2. As we have the process equation which is P equals to f of V, this can be written as integration of f of V dV from V1 to V2. If you just have a look on this expression here, you can see this is area under PV curve or area between PV curve and y-axis. You must also keep in mind there is a PV curve and volume axis. Now in the situation, say if there is the situation, a gas is changed from initial state S1 to S2 corresponding to a curve like this. Now in this situation we can see the curve is moving from left to right. That means the volume is expanding from V1 to V2. As we already discussed, when volume increases, work is done by the gas onto the surrounding atmosphere. So if we just calculate this area between the PV curve and volume axis, this area corresponding to this expansion, we can say work done is equals to this shaded area, and here we can say work done will be positive because gas is expanding, work is done by the gas. Similarly, if the situation is given like this, if in a particular case initial state is of higher volume, V1 is more, and the gaseous state is changed from S1 to S2 like this, and here V2 is less. So you can see the curve is moving from right to left. So in this situation, the gas is being compressed. In case of compression, we can say this area will be negative because volume is decreasing, gas is being compressed. So we can say work is done on the gas. You can keep in mind this is the situation when work is done by gas because gas is expanding. Gas is being compressed, so this is a situation when we write work done on gas. And the situation again, and the magnitude of work done, we can write this shaded area, and here work done will be negative because whenever work is done on the gas, the work is taken negative. So directly by using indicator diagram, we can calculate the area between the diagram and volume axis, and this area gives us the magnitude of work done. Positive or negative, we can check whether the curve is moving toward right or toward left corresponding to expansion or compression.